Okay. So here in mechanics, we will be discussing both statics of the fluids as well as the dynamics of the fluids. So the statics we will be covering under hydrostatics, and then the dynamics, which we will be studying the next lesson, which we want to study the fluid dynamics when the fluids are in motion. So that is fluid dynamics. So today our objective is to cover all the theories related to hydrostatics, right? Okay. So hydrostatics, when it comes to hydrostatics, so it involves a fluid. So let's start writing with the subtopic fluid. So write down the subtopic fluid. So in Sinhala we call Tarla. Okay. So fluids, what is a fluid? Anyone tell me? What is the fluid? Okay, good. Any other answers? Yes. Liquids and gases. So when I ask what are fluids, then you can say liquids and gases. But if I ask what is a fluid, then it is we can't say like that. So fluid means when the particle now for example we know all the materials made of particles like atoms and molecules, right? So these molecules, if they are can move freely here and there within the medium, then it is a fluid. Now, for example, if I take a solid particles, they are fixed in certain positions, right? So there is no any relative motion between the particles, right? So therefore, solid is not a fluid, but we know in liquid and gases, the molecules can move here and there freely. So therefore, the liquid and gases are fluid, right? So let's write down under that. The atoms or the molecules of a material can move freely through the medium or the material through the medium of a fluid. Example, we can write liquid and gases. Liquids and gases. Okay, so let's write down some characteristics of fluid. So write down under that subtopic characteristics of a fluid. So fluids doesn't have a certain shape. So it doesn't have a certain shape. Fluid doesn't have a certain shape. And next point. Fluid has a finite volume uh, full stop, and write down under that, a liquid has a certain volume, but a gas doesn't. So when we say fluid, we are talking about liquid and gases. So a liquid has uh, a value volume, but the gas doesn't. Last point, the fluids can flow. Fluids can flow. Okay, write down the next topic. Compressible fluid. Okay, what is the meaning of compressible fluid? A compressible fluid means, imagine, for example, there is a liquid or gas. Okay, so in general, I'm saying the word fluid. So let's imagine a fluid is inside a piston, and if you can apply a force and change the volume. Now, for example, there is a certain volume of a liquid. You push it, apply a force, and you decrease the volume. So if that can be done, then such liquid is known as compressible liquid. Okay, so let's write down uh, under the compressible fluid, the volume, the volume of a liquid, a volume of a fluid. Yeah. In general, we write volume of fluid can be changed upon applying an external force. The volume of a fluid can be changed upon applying an external force. Then we say that the fluid is compressible. Then we say that the fluid is compressible. Okay. So this is compressible where we can apply a force and change the volume. We can squeeze or expand it. Okay. Then the other type is incompressible. So write down incompressible fluid. So most of the liquids we consider they are more like compressible. Okay. So here you can write example many liquids. Okay. So incompressible fluid, the volume cannot be changed. Sorry, compressible here gases, many gases. Because gas only very easily we can change its volume, right? You will study the gas laws and all, the Boyle law. If you decrease the volume, pressure increases. So the gases, the volume can be changed, right? Can easily. Okay, so many gases are, almost every gas are compressible. And incompressible fluid, the volume cannot be changed, cannot be changed. The volume cannot be changed by applying an external force. The volume cannot be changed by applying an external force. The volume cannot be changed by applying an external force. Okay, so the liquids, like if you take a liquid, it's for example, it is very difficult to change the volume, unlike a gas. Compared to gas, the volume change in liquids will be very small. So in most of the cases, the liquids we can consider as, it's a approximation, we can consider as they are incompressible. Okay, so we can write uh, liquids, or we can say some liquids some liquids can be considered as incompressible. Okay. So far now we studied what are compressible fluids. We can compressible means we can change the volume by applying an external force, and incompressible means we cannot change the volume by applying an external force. All right, so write down the next topic, pressure. Write down pressure. So what is pressure? Can write the force per unit area. The force per unit area. Okay, so pressure equals force over area. So P equals X over A. P equals X over A. P equals F over A. Okay, tell me the pressure is a vector quantity or scalar quantity? Okay, I got a message. My video is lagging. Does everyone, is it same for everyone or only for you? Okay, let me know whether my video is lagging. If it yes, drop a message in the chat box yes. Otherwise, you can say no. It was lagging, now okay. Now okay. So, right. Video lag වෙනවනම් කියන්න so that I disconnect from my desktop. Okay. But if I disconnect, I won't be able to see your questions. In that case, you have to unmute and talk because I'm using the back camera. Okay. Since the Wi-Fi, the data is consumed by both phone and the desktop, it may lags. So sometimes, so if it's happening and if it's kind of hard, then please let me know. So I'll do it. Yeah. All right then. So pressure, let me know pressure, is it a vector quantity or scalar quantity? Pressure is a vector quantity or scalar quantity? Okay. So the pressure is a scalar quantity. Pressure is scalar. I got few answers saying pressure is a vector. Pressure is a scalar quantity. Okay. Pressure is scalar. Okay. So here we can write rearrange this formula. F equals E times A. F is vector. Pressure is scalar. This is vector. Now what about A here? Is it a vector or scalar? The area. Area, is it a vector or scalar? I got only 2 response out of 7. What about the others? Area, is it a vector or scalar? Okay, here you can see force is vector and this is scalar. Therefore, area should be vector. Area is a vector here. See, because here in the left hand side we have force vector and this is scalar. Scalar means movement, or direction. Right? If you multiply by another scalar, let's say area is also scalar. Scalar times scalar, how can we get a vector? මෙයාටත් දිශාවක් නැහැ, මෙයාටත් දිශාවක් නැහැ. So both of this don't have direction, but their product is only having a direction. That is nonsense. I mean, it won't happen, right? Because yeah. So therefore, one of this must be a vector. But we know pressure is scalar. So therefore, here area is a vector. Okay. So F equals P times A. So this is the vector form of this equation. Okay. So if area is a vector, it should have a direction, right? Now, for example, let's say I'm applying force on this whiteboard, right? So let's say my cross-sectional area, this cross-sectional area is capital A, okay? Or else, let's say take a value of something like 5 centimeters square, 2 centimeter, 4 centimeter, let's say something around 10 centimeters square, okay? So when I apply a force, okay, so there is a area of contact which is 10 centimeters square. So let's say this is the that area that is contacting with the board. Okay. So I apply a force of let's say 20 Newton. So then now the force has a direction. I'm applying the direction into the board, right? 20 Newton into the board. Therefore, this area is actually have a direction at the midpoint. You have this area you can find the geometric center. So something like here. If it's circle, finding is easy, it's midpoint, right? But here in this shape, let's say this is the center. On that center point, the area vector is pointing towards into the board. So that when I apply a force, let's say F, or I say apply a, yeah, so then I can find the force is equals to pressure times the area. So the force is in the direction of the area. Okay. So area is a vector. Okay. I think in 1 year also they have been asked out of this which is a vector quantity. So the answer is area. Okay. Okay. So the equation to find the pressure is P equals to F over A, force over area, force per unit area. So the unit area is 1 meter square because the SI unit of area is 1 meter square. Okay. So then the unit force per area, so Newton per meter square, and dimension of P, you should be able to say this ml minus 1, T minus 2. Okay. I'm gonna make a, if you are still trying to find the pressure by writing the formula and get the dimension, that means you haven't studied enough. I mean, that is not enough for B. Okay. If you want to take for A by now, you should be able to say the dimensions of these physical quantities like without thinking. Now, for example, if I ask you, uh, for example, let's say, yeah, what is the planet you are living in? Earth. Would you think no, right? So likewise, if I ask you what is the dimension of pressure, ml minus 1, T minus 2. Of energy, m squared. Okay. All right. So dimension is. Is it okay now? Okay. So let's do some questions. For example, let's say there's object of mass 20 kilogram and the cross sectional area of the base is 0.5 meter square. Okay. So find the pressure. Okay. Find the pressure exerted on the ground. Find the pressure exerted on the ground. So we can find pressure P equals F, which is so the normal reaction force here R, okay, and here there is the normal reaction force and the weight of this mg, okay. So if you consider the equilibrium of this object, so the force acting on this object is only these two forces. So R is equals to mg. So this R is equal to this according to Newton's third law. So this R is equals to then mg, so 200 Newton divided by cross sectional area 0.5 meter square. So P equals to 400 newtons per meter square. By the way, I forgot to tell you the unit is Newton per meter square. Also, we can write Pascal. Capital PA, Pascal. Right? Pascal is also a SI unit for pressure. Newton per meter square or Pascal. Okay. So this is an example. So the next one. Let's say this time we have a inclined plane, angle 60 degrees, and mass is, let's say, 20 kilogram, and the cross-sectional area 0.5 meter square. The same question, find the pressure exerted on the plane by the object. Okay, try this one. If you're done, you can share your answers in the chat box. Okay, I'm getting the correct answers. Good. So we know its weight downward in G, and we can resolve this into two perpendicular components, this side. So this is mg plus here this angle is 60. So this will be 30, this 30 and this 60 again. So this mg cos 60 and mg sine 60. So this, if you consider this component, it is parallel to the area vector. So therefore, this doesn't make any pressure on this surface, but this one is perpendicular to the this area. So there will be a pressure. So we can find that pressure P equals mg, which is the weight, 200 into cos 60 divided by the cross-sectional area, 0.5. So cos 60 is half and half cancel. P equals 200 Newton. Okay. And let's write down a note. Pressure is inversely proportional to the area. Pressure is inversely proportional to the area. Pressure is inversely proportional to the area. Now, for example, let's say if you consider a car tire makes pressure. I mean, you can see the rest of the cars there. Here, the pressure is something around 200 kilo Pascal. Okay. The 20 kilo Pascal. And if you consider the women heels, okay, so here it makes 2000 kilopascal. And male thing. So here the area is very small, so it can take up to 5 million kilopascal the pressure. Here by hand we can apply a pressure of something like 100,000 kilopascal and can get pressure of this much, because here we have a large area and here the area is small, so the pressure will be very large. Okay. These values no need to remember, just to get some impression idea about the how pressure varies with the contact area. Okay. Okay. So let's write down the topic: pressure in liquids. Pressure in liquids. Okay. So let's say we have a liquid container, and there is liquid here. Okay, the board is blurred. Yeah, by the way, if there's anything, please drop a message to the Knowledge Institute, because I'm not be able to see the screen as I have connected to the back camera. Okay, all right. The video is loading. Is it okay now? Okay. So the pressure at a certain point on the liquid, okay, let's say P, is depends on certain factors. Okay. Now the pressure at this point is mainly due to the weight of this water above that point. Okay. The pressure at a certain point inside the liquid is due to the weight of the liquid above that point. So let's write down the pressure, at a certain point, at a certain point, the pressure at a certain point inside the liquid, is due to the weight of the liquid above that point. Is mainly due to the weight of the liquid above that point. The weight of the liquid above that point. Okay. So now let us try to find the pressure at this point. Okay. So in order to find the pressure at this point, I'm considering a hypothetical cylinder. Now this is the container. Within that, I consider a hypothetical cylinder. Okay. So let's say this cylinder, the height is h because the depth to that point is h. And let's take this area is capital A, and the density of the liquid will take rho. Okay, and we know we are in the earth talking about these things on earth, so the gravitational acceleration will be g. Okay. So now I can write the pressure here, P is equals to force over area. Force is due to the weight, this part. So this weight I can write, the weight is mg. So this one has a mass m. Okay, mg over area is capital A. And the mass I can write, mass is equals to volume times density. The mass equals volume times density. So volume AH, cross sectional area into height is volume times density. So therefore, pressure is equals to AH, pressure is equals to AH rho G divided by A. So this A and this A cancel. P equals H rho G. So this one gives the pressure of the liquid at this point. So you can write this down. Okay, and then write the pressure of a liquid depends on the pressure of a liquid depends on. So it is depends on what? So the depth, the first one is the depth, and second point, density of the liquid, and third point, the gravitational acceleration. And if you take the same liquid container to the moon, at this point pressure will be less in moon than that is in the earth, because in moon the G is smaller than earth. So in moon here the pressure at this point will be less. Okay. Then let's write down some important facts regarding the pressure uh, in liquids. Okay, can take, hope you've done this. So you can write important facts or notes with important facts. Okay, the first point, the pressure of the liquid, the pressure of a liquid, pressure of a liquid, the pressure of a liquid does not depends on the shape of the container, shape of the container does not depend on the shape of the container. Now, for example, say I have a yeah, use say so, and also the another point, when a liquid contains in any container, we know that water level will be safe. Okay, this fact is used to do leveling during the constructions. Okay, so can draw something like this. Okay, so here is the point A, and here point B, point C, point D, all are at the same level. So I can write pressure at A equals to pressure at B equals to pressure at C equals to pressure at D. Okay, write down. Okay, so second point, you can write uh, in a liquid container, pressure at the same level at at any point on the same level are equal. So here one liquid container. So here I take this point x, the same height here y, here z, and here b. So then we can write here px equals py equals pz equals pb. At the same level, the pressure will are equal. And the third point, okay. So third point, we know the pressure is a scalar. Pressure is scalar quantity. So it doesn't have a direction. But due to the pressure, it exerts, but due to the pressure, it exerts a force on the surface of the container. It exerts a pressure, but due to the pressure, it exerts a force perpendicular to the surface of the container. So pressure is a scalar quantity, so it doesn't have a direction. But due to the liquid pressure, it exerts a force perpendicular to the surface of the container. For example, let's say is a lake and there's a boat. So here, due to the liquid pressure, the pressure of the liquid, it exerts the force. The force is perpendicular to the surface. Okay. So you can quickly draw this. Okay. You can take a screenshot if you haven't completed. And the fourth point is the pressure increases with depth. The pressure increases with depth. So let's say if we have a liquid container. So the here point A and the point B is point C. So I can write B and PC. Here the pressure is maximum. Okay. And also, if I take a liquid container and insert some holes here, here, and here. So the liquid is is so here the ejecting velocities will be higher here. This fact is not so important for us to study in hydrostatistics, but in fluid dynamics, this fact is useful. Here the velocity is by right. It says here V2 and V3 and VC. So AB, VC. So this is nothing to do with the hydrostatics, but this will be we will be studying in fluid dynamics. Okay. Hi guys, can you hear me? Okay, thank you. All right, so let's say we want to find the pressure at this point. So we know how to find the pressure here. So let's say this depth is H. So the pressure at this point will be uh, H rho G. That is this pressure. But then again, we have a atmospheric pressure. The atmospheric pressure we normally mark with pi. So therefore, the pressure pi plus H rho G. I add these two pressures. So the pressure at this point is 5 plus H rho G. So the pressure P equals 5 plus H rho G. So we can write this down. Yeah. So let's say you want to find the pressure here. Okay. Here the pressure we know it's due to the weight of this liquid. So that is we already found that it is H2O. Right? We already discussed that. And apart from that, we have the atmospheric pressure as well. So here we write atmospheric pressure. So therefore, the total pressure is equals to atmospheric pressure plus the pressure due to the uh, water column about the liquid column about this point. Weight of the liquid column about this point. Okay. So therefore, the pressure here P is equals to 5 plus H over G. Okay. Yeah. And the atmospheric pressure, the value, the phi, which is the atmospheric pressure, has a value of it's approximately equal to 180. No, it is equals to 180. Yeah, one atmospheric pressure. Okay. And this 180 which is atmospheric pressure, is approximately equal to 10 to the power 5 pascals. 180 is equals to 10 to the power 5 pascal. You can note down this. Okay. What are the topic of barometer? So write down, a barometer is used to measure the atmospheric pressure. A barometer is used to measure the atmospheric pressure. A barometer is used to measure the atmospheric pressure. Right. Now, let's say I got the barometer. Okay, so here this is a barometer. Here we have a vacuum. Vacuum. Okay, tell me what is a vacuum means? What is a vacuum? Okay, so vacuum means no particles, right? So there is no air or any particles, right? So what can you say about the pressure in a vacuum? Zero. Very good. So in order to exert a pressure, there should be particle. Now, for example, if there's a liquid only, this liquid will make a pressure on the container. Or if there's air only, the air will make a pressure on the balloon, for example. Right? So there should be particles, right? A particle should interact, make a contact with certain things to make pressure, right? So if there is no particles means it cannot exert any pressure. So the pressure is zero, right? So you can put a notes in a side note. The pressure of a vacuum is zero, right? Okay. So here zero pressure. Okay, but here this exerts atmospheric pressure. Okay, so atmospheric pressure. So as the atmosphere pushes the liquid downwards, what happens? There is no option. The liquid will move above the this column. Okay, and here this liquid is mainly used mercury. Plus mercury. Okay. Can you tell me why we use mercury? Any idea why we have to use mercury? Less density? No, mercury is denser than other liquids, right? Because it's a metal. It has a high density compared to other liquids. Why we use mercury here? More expansivity. How the expansivity is here? No, there is no any change in temperature and effect we consider here. Any other answers? Get better, probably. But anyway, the reason we are using mercury is it is less volatile. So now, for example, if you use something like water or alcohol, what happens? It will evaporate. So there will be a what vapor pressure. So the pressure won't be zero. So it will cause an error in our calculations. So therefore, we use mercury because it has a high cohesive forces. The force between mercury molecules are super strong, so strong, so that the mercury molecules won't evaporate. It has a large cohesive force. Now, for example, if you take the mercury and put it some drops, if you drop it down, it will form as spherical balls. Whether you should not hold mercury from bare hands because it's a toxic material. Okay, do you understand? The mercury particles have large intermolecular forces. We call it the same type when it is cohesive force. The cohesive force of mercury is large, make that less volatile, won't evaporate, unlike uh, water and alcohol. So that is the main reason why we are using mercury, because we want to maintain a zero pressure here. Is the video is lagging, guys? Hi all, can you hear me? Okay, thank you. Okay, so here we use mercury mainly because to maintain a zero pressure here. Otherwise, if you use like uh, water or alcohol, uh, it will vaporize, right? Evaporate. So there will be a vapor pressure, right? So it will cause an error in our calculation. And the other reason is mercury's. So main reason it is less volatile, and second reason it is high dense, right? Because I told you that 1 atm is 10 to the power 5 pascals, newtons per meter square, right? That means 100 million, 100,000 pressure, right? 100 kilopascals. So because it carries the entire the atmospheric weight, right? Yeah, weight. So you can see the atmospheric pressure is so big. So therefore, if you use like water, the water column will rise to a height, I think around 9 meters, 8 meters, something like that. But since we are using mercury, it is heavy. It will only lift up to 76 milli, centimeter, 76 centimeter, something like 76 centimeter can be, yeah. So you know 1 meter ruler, which is 100 centimeter. So you can get the rough idea what is 76 centimeter means, right? But if you use the water, it is less dense. So the water rise to a height something like meters, like 3 meters, 7 meter. I'm not sure. Something between 3 and 9. We can calculate if you want. We can calculate the height that the water will rise. Uh, we will do that. I will give you an example. Yeah. All right. So first reason, the mercury is less volatile. That's why we use mercury so that here we can maintain a zero pressure. The second reason, mercury is high dense, so that it's easy to construct. We have to have only like 1 meter size of apparatus. But if we use water, we want to make it like 4, 5, 6 meter apparatus to handle. So it will be uncomfortable, right? So these are the main two reasons why we use mercury. So you can note down this, okay? So you can write the main two reasons why the mercury is being used. One is less volatile, and then high density. High density. Or density is high. So these are the two reasons mainly why we use mercury as the, and also you should be able to explain. So the explanation here, if you use volatile liquid, so it will evaporate and gives a vapor pressure, which cause an error in our calculation. Okay. The other reason for this, the reason if you use a less density liquid, then the rise in the liquid column is so high. So maintaining such apparatus is uncomfortable, inconvenience, right? All right. So okay. So now let's see how to find the calculate the atmospheric pressure using a barometer. Okay. So I mark here the atmospheric pressure file, and I consider 2 points. So here is point A and this point B. And we know at a same level the pressure are same. So it's same liquid in the same container. So here and here pressure same. So we can write P A equals to P B. So PA, the pressure at A is due to, now here the atmosphere exerts a pressure here. So we can write phi is equals to pressure at B is due to pressure of this liquid column, mercury column. So H rho G. Now if in case if there is a vapor pressure, we have like that. But we are using mercury and here zero pressure. So it will be H rho G. That's all. So therefore, the atmospheric pressure we can find using this. I equals H rho G. And let's try to calculate this. So here this one show H equals 76 centimeter. You may construct a barometer using mercury. The height will show 76 centimeter. So now let's try to calculate this pressure value. Okay. So phi, the atmospheric pressure, is equals to 76 centimeter. We want to write in meters, 0.76 into the density of mercury. If I'm correct, 13,000. Let me check. Yeah, it is 13,600. 13,600 into G is 10. Phi equals, so 0.76. So we'll multiply these two with this. So 76 into 136 into 10. 76 into 136. Use the calculator. 96 into 136. 10,336. 10,336 and multiplied by 10. So we have 0 T, T, 6, 0. So it is 1.03 into 1, 2, 3, 4, 5. 10 to the power 5. So here I wrote this in meters and then this is in kilogram per meter cube and then so all in SI units, then I will get in SI unit Newton per meter square. So that's how you can see 1 atm is approximately equal to 10 to the power 5 Newton per meter square. Or it is equals to 1.03 into 10 to the power 5 Pascal. So we can write 1 atm is approximately equal to 10 to the power 5 pascals. Okay, write down. Okay, so write down this question. Find, okay. If the liquid, no, wait. Yeah, if the liquid used in the barometer is water, if the liquid used in the barometer is water, if the liquid used in barometer is water, comma, Find the height find the height that water will rise in the barometer. So assume the water does not evaporate. So otherwise we had to calculate that vapor pressure as well. Yeah, sure. If the liquid used in barometer is water, find the height that water will rise in the barometer. Find the height that the water will rise in the barometer. And in brackets you write assume water does not evaporate. Assume water does not evaporate. Okay. Okay. Can you try this? Okay, I already got an answer and it seems it's correct. So what you have to do, so phi equals h rho g. So phi equals the phi is now we know the pressure value, which is we can take frequency of 5 Pascal. 5 inside h we want to find the density of water is 1000 into g is 10. So therefore h equals 10 to the power 5 divided by 10 to the power 4. So h equals 10 meter. So see, if you want to construct a barometer using water, you should have apparatus which is 10 meter long. For example, if you take your house, each floor is roughly 3 meters. So 10 meters is something like more than 2 stories, right? So that's why we are using high dense liquid for a barometer. So the more high dense is the mercury because it's a metal. The density is high. Okay. Write down the next question. Find the pressure. Find the pressure at the depth of 20 meters. At the depth of 20 meters. The depth of 20 meters in a lake. Right. So that's the question. Now you know all the data, right? So the lake needs water. So you know the density of water, and you know the atmospheric pressure. So I find the pressure at the depth of 20 meters. can put your answers in the chat box if you're done. I'm getting different answers. 4 into 25, 3 into 25. Okay, so here the answer is I don't need to do any calculation because now from my knowledge, I know it will be 3 into 10 power 5 Pascals. I'll explain how I get it without doing any calculation, but first I will do it in the normal way. So here's the lake at the depth of 20 meters. We want to find the pressure. The atmospheric pressure is 5. That is equal to 10 to the power 5 pascals. Okay, so the pressure is fine. I can write P plus atmospheric pressure plus right 5 plus H rho G. 5 plus H rho G. Okay, so 5 is 10 to the power 5 plus H 20 density of water 1000 10 to the power 3 into G is 10. Okay, so here we get 10 to the power 5 plus 2 into 10 to the power 5. So we get 2 plus 1, 3 into 10 to the power 5 pascals. Okay. Right. Now I tell you how I got this without doing any calculation, because in the previous question we found that atmospheric pressure is equal to 10 meter of water column. Right. So that means 10 meter of water corresponds to 10 to the power 5 pascals. So now 20 meter means that double the pressure. So 2 into 10 to the power 5 pascals, and additionally we have the atmospheric pressure, so 3 into 10 to the power 5 pascals. Okay. So these techniques that you have to improve so that you can go faster in your MCQ papers. Okay. Right. Do you understand? Good. And now let's see what are the units of measuring pressure. So other units of pressure. We know that already is a unit. So unit is Newton per meter square or Pascal. The Newton meter square is defined as Pascal. So Pascal is the pressure exerted by 1 Newton of force acting on 1 unit area, 1 meter square. Okay, that's the definition of Pascal. Right. So other units of pressure we have now we discuss in terms of height of mercury. So that is we write Hg centimeter. So Hg centimeter is a unit of pressure. That is 1 unit, or Hg millimeter. Hg centimeter, or we have Hg millimeter. So we calculated that Hg centimeter is I think 1.03 into 10 power 5 Pascal. This value will sometimes vary because Now I take G as 10, but if we take more accurately 9.81, so this one have a different value, right? So roughly as approximation, we can have 1 Hg centimeter is 10 to the power 5 Pascal. That's what you have to remember, right? So this is 10 to the power 5 Pascal. Okay, and then Hg millimeter is actually so 10 millimeter is equals to 1 centimeter. So therefore 0.1 Hg centimeter, right? So therefore this is actually 10 to the power 4, no, 0.1 Hg. So we are 10 to the power 4 Pascal. And Hg centimeter, Hg millimeter, and we have 4 bar. Yeah, bar. 1 bar is equals to this 1 Hg millimeter. 1 bar is equals to that is also again 10 to the power 5 Pascal. And 1 atmosphere, 1 atm, that is also 10 to the power 5 Pascal. So these are approximate values. The actual value 1.03 or 1.36 depending on what's the G you are taking. Okay. But then again, they won't ask such questions in your exam. In fact, in exam also, if they give 1 bar, you convert as 10 to the power 5 Pascal only. Otherwise, they will give the value. 1 bar is equals to 1.32 into 10 to the power 5. Like that, they will provide the value. Or if they didn't provide the value, you can take 1 bar is equal to 10 to the power 5. 1 ATM is equal to 10 to the power 5. Are you clear? Okay, so these are the units of pressure. Now, the something with this. Hold on. Yeah, actually, here we have to divide by because 76 Hg centimeter is equals to 10 to the power 5 Pascal. Yeah, so 1 Hg centimeter is, take this number, 10 into 10 to the power 4 and divide by 700 into 10 to the power 3 plus divide by 76 here. So we have to take this value as the Hg centimeter. Yeah, hold on. So 100 divided by 76, we get, we'll use the calculator. Yeah, that is 0.315. Yeah, so here this is actually these two ones. 1 Hg centimeter is 1.3 into 10 to the power 3 Pascal. So millimeter is 1.3 into 10 to the power 2 Pascals. And these are correct. 1 bar is 10 to the power 5 Pascal, 1 atm. 10 to the power 5 Pascal. Okay, because we know 176 centimeter Hg is only equals to the atmospheric pressure, 10 to the power 5 Pascal. And also, you should know this 76 Hg centimeter is equals to 760 Hg millimeter. Yeah, this also you should be knowing. 76 Hg centimeter is equals to 760 Hg millimeter. Please correct these two. Yeah, so I'll explain again. We know we found that 76 Hg centimeter is 118, which is 10 to the power 5 pascals. So therefore, to find the value of 1 Hg centimeter, we have to divide both sides by 76. So 76 divided by 76 here 1, then this number we have to divide by 76, then we get 1.3 into 10 to the power 3 pascals. Is that clear? Just write on the topic, pressure in gases. Okay, so pressure in gases. Now, for example, just imagine we have a balloon. You blow a balloon. So we trap some air. Right? What we do in blowing a balloon, we put air into the inside the balloon. Okay? We send air molecules. So what happens? So if I blow more and more air into it, more and more pressure will be there. So it will expand due to the pressure. It exerts the force, and then it will expand, right? Though, so there will be equilibrium, right, in balloon. One is the air, due to the air pressure, it exerts a force perpendicular to the container. I mean the wall of the balloon. Okay? And also there will be a tension force due to the stretching. So there will be a counterbalance. But anyway, here what happens is these molecules, gases, have kinetic energies. They collide with the container or the wall. Now, for example, if you take another gas container, so these gases randomly in high speeds collide with the wall of the container in random directions. Okay, the total movement is random. I think you may have studied if you are doing chemistry, the kinetic theory of gases. So these gas molecules, they move in random direction with random speed. high speeds, right? So they will collide with this wall of the container. So how many particles are there? Now if I take 1 mole of some substance, we have roughly 6 into 10 to the power 23 particles. So if I take such a balloon or some gas container, this particle is greater than this number, right? Will be greater than this number. So we have large number of particles. So large number of particles make collisions with the wall of the container. So during this collision, there will be a momentum change. So therefore, there will be a force acting on the wall of the container that is perpendicular to the surface. Okay. Right. So we can write now. Let's say this is the wall container. Now, at a time, there will be like millions of particles colliding, but I consider only one particle colliding here, the wall. Let's say the mass is m, and let's say the velocity is v. And if I assume the collision is elastic, the same v speed will be there on the volume. Okay. So then I can consider the change in momentum. Let's say if this angle is theta. Excuse me, give me a second. Okay. So if I consider this angle theta, we have we can resolve this v cos theta and this side can be sin theta. And then I'll draw a large. I consider only the one particle or the wall. Okay, so we can resolve this. Then in this direction we have mv cos theta. This direction mv sin theta. Since this angle theta, this angle also will be theta. And also here, this component mv cos theta, mv sin theta. Okay. So if I consider the gas molecule, I consider in downward because the momentum is a vector quantity. You have to consider a direction. So I consider downward change in momentum delta T5 in downward. So final momentum is mv sin theta. Final momentum minus initial momentum mv sin theta. So in this direction, there will be no change in momentum. It's zero. But if I consider this direction, delta Px, so final momentum is mv cos theta minus initial momentum. So I'm considering this direction, but the initial momentum is in this direction. So we have to write minus mv cos theta. So here minus and minus plus. So we get 2 mv cos theta. So this is the momentum change due to this collision. Uh, so I write here. So then due to this momentum collision, we can find the force. The force is delta E over delta T. So there will be a force exerted on the particle because I'm considering the gas molecule. So delta P is 2 mv cos theta over delta T. Right? That means during the collision, right? Collision. So here this is before collision. This is after collision. So at collision is the wall, the container is the gas particle. So we can see there is a force exerted on this direction because the momentum changes in this direction. The Newton's second law, the force acting on an object is directly proportional to the rate of change of momentum, and the direction is in the direction of the changing momentum. So this is F. Now, according to Newton's third law, every action has equal and opposite reaction. So there will be a force acting on the wall of the container. Okay. So you can draw this and then you can write this. Write down this and then this one. And then I will give a note. Yeah. So here this is before collision and after collision, and then you can consider the change in momentum. In vertical direction, no change in momentum because initially also it's moving with mv sin theta. After collision also mv sin theta, so change in collision momentum is zero. But in the direction perpendicular to the wall, we can see there is a change in momentum, right? So this is the reason why the force due to the pressure is always perpendicular to the surface. So here due to this there is a in the perpendicular direction to the collision we have a change in momentum 2mv cos theta, right? So then according to Newton's second law, the force is the rate of change of momentum. So F equals 2mv cos theta over delta t. So then at the collision we have this force, right? Due to this force only this momentum has changed from mv cos theta to mv cos theta. The change is 2 mv cos theta to the right side. Okay, and so we can draw the diagram at the collision. So there is a force acting on the gas molecule. So according to Newton's third law, every action has equal and opposite reaction force. There will be a equal force acting on the wall of the container, right? So due to this, there will be a pressure. So that pressure we can write P equals F over A, where A is the effective area of the collision. Like you can see at the collision, there is some area is uh, contacting the surface, right? So that area, so if P equals F over A. So then I can write P equals F is 2NB cos theta over delta T times A. Right. Raise your hand if you finish writing up to here. So first you have to draw this, and then second you have to write this, and this is the third. Okay, then let us write. When a gas is inside a container, when a gas is inside a container, the gas molecules make collisions. The gas molecules make collisions between each other. The gas molecules make collisions between each other, as well as they make collisions with the wall of the container. They make collisions with the wall of the container. They make collisions with the wall of the container. All right. Due to these collisions, there will be a force. There will be a force exerted. There will be a force exerted. There will be a force exerted on the wall of the container. On the wall of the container in a direction perpendicular to the wall of the container. So there will be a pressure exerted on the wall of the container. So there will be a pressure exerted on the wall of the container. Okay. Now, by the way, in this lesson, none of these is much important, but these things I think already you may have come up with in mechanics, right? With the momentum change in collisions as well. Anyway, so here our main key takeaway is the pressure of a gas is the pressure exerted on the wall of the container by the gas. Okay. So I will give you that note. So you can put a highlight and write, or you can write inside a box or something, whatever. You can highlight and write. The pressure of a gas, the pressure of a gas in a container, the pressure of a gas in a container is the pressure, is the pressure exerted, to the wall of the container, the pressure exerted to the wall of the container by the gas, by the gas. So now, for example, let's say we have a container and there is a gas, and the pressure of the gas is, let's say, P, and it is the same as the pressure it exerts on the wall of the container. And it is always perpendicular to the wall of the container. Okay. And also this is regardless the shape of the container. Let's say we have some shape. So here everywhere pressure is P. Pressure of the gas here P, here P. The pressure exerting P and exerting here P. The same pressure will be everywhere. So any place of this container will be have the same pressure. Okay. So you can put a note and write the pressure everywhere on the wall of the container is same and same as the pressure of the gas. The pressure everywhere on the wall of container is the same as the pressure of the gas. Okay, so let's write down subtopic manometer. Write down it is used to measure the pressure of a gas. It is used to measure the pressure of a gas. Okay, so let's say here's the gas, and here we have our uh, mercury, and there will be H difference due to the pressure. So let's take this height difference uh, H. Okay, so we know for a liquid, the pressure at the same height, same level are same. So I take this point A and here point B. So I can write the pressure at A is equals to pressure at B. We will take the atmospheric pressure phi. Okay. the gas pressure is P. So here the pressure A. Now we know if a gas is inside the container, everywhere the pressure will be the same. So here the pressure exerted on this wall of the container is the same as the pressure of gas. Here the wall it will same pressure on the exert. Likewise, now this also you can think as a wall of the container, so that then here also it exerts the same pressure, right? So then pressure at A is P, that is the pressure of gas. Okay, is equals to pressure of B. The pressure here is equals to H rho G plus phi. H rho G plus phi. So then we get P equals H rho G plus phi. So from this, we can find the pressure of the gas, because now we know how to find the atmospheric pressure. And we know that we can take this value to find the pressure of gas. Right now, for example, let's say, as an example, let's say H is equals to, example, let me take H equals 10 centimeter. Okay, for example, let's say 10 centimeter. Okay, I didn't understand how to get the pressure here as P. Okay. Now, in the previous part, the pressure of a gas in a container, we explained, right? If a gas is inside, okay, regardless the shape, okay. If the pressure of a gas means it is the pressure that exerts on the wall of the container. The same pressure. Now let's say this pressure here, gas of pressure is 2 Pascal. So here it exerts a pressure 2 Pascal. Here exert a pressure 2 Pascal. Here exert a pressure 2 Pascal. Here exert a pressure of 2 Pascal. Here also 2 Pascal. Everywhere it will have the same pressure as 2 Pascal, right? That's what we wrote in the previous part. When a gas is the first point, the highlighted point, we wrote the pressure of a gas is the pressure that the gas exerts on the wall of the container. Pressure of gas is the pressure that it exerts on the wall of the container, right? So, and also the next point, we wrote the if a gas is inside a container and its pressure is, let's say, P, then everywhere it exerts same pressure on the wall of the container, right? Now, if you consider this part, now here the gas, its pressure is P, so that means everywhere it will make the same pressure on the wall of the container. So here also, then you can think, now if I zoom this part, so you can have, here this point is A. So here it makes a pressure of P. Here the pressure is P. Here also pressure P, because it's the same gas in the, so it is one closed container. So everywhere pressure is P. So pressure at A or equals to P, and pressure at B is, here the pressure is H rho G due to the weight of this liquid column plus atmospheric pressure. Is that clear now? Okay, good. Now assume the height is h, then I can write the pressure of a gas P equals, so 10 centimeter Hg, so Hg centimeter, plus atmospheric pressure is 76 centimeter Hg centimeter. So therefore the pressure of the gas is 86 Hg centimeter. If you want, you can convert this into pascals. Because G centimeter, we know, right? 1.3 into 10 to the power 3 or 4. I'm not sure. You can check your note. 1 G centimeter is equals to, okay. Or else what you can do, you can put the values here. Like, so 10 centimeter means 0.1 rho 13,600 into G is 10 plus 5 is 10 to the power 5. You get this value that will be in, you take this value, so 13,600 plus 100,000. So we have 30,600. If I have this 113,600, so it will be 113.6 kilopascals. So this will actually equals to 100. If you convert G centimeter to pascal, you will get 113.6 kilopascal. Is that clear? Is it clear for everyone? So rather you can keep the answer in HG centimeter because that is also you need to measure the pressure, right? So here the height difference is 10 in mercury. So it should be mercury, the liquid should be mercury Hg, right? So the pressure will be 86 centimeter Hg. Okay, and then let's do one problem from YouTube. YouTube. Okay. So here I put two different liquids. For example, uh, water and yeah, let's say water and oil. So oil is less dense, so it has to be higher weight. Okay. So we can see here in this tube, let's say the height of this is h1. Height of this, I take water HW or H4. oil. So the density of rho W is 1000 kilogram per meter cube. Rho oil, I think oil has less density, something around 700. Let me check. I have to Google it. Yeah. Let's see. The density of most oils between 0.7 and 0.9 gram per centimeter cube. That means we take 700 kilogram per meter cube. Okay. Okay. So I'll give you as a question. First, we will write in algebraically. Okay. Now, if two liquids are static in a U tube, right? So it is static, like it's balanced now. Okay. Then the condition here should be the pressure both sides should be same. Here the pressure should be same. Let's say at this point A and this point B, they are just closer to the common surface, intersurface of water and oil. Okay. So here then it should be satisfies this condition. EA should be equals to B. So the pressure at A is due to the weight of the oil column. So we can write that is H rho naught G equals to here H W rho W G. The G and G cancel. We get H naught rho naught equals to HW rho W. Okay. Now this is for water and oil, but for any liquid, like okay, I hope you can understand. For any liquid, let's say it is H1 density rho1 and height is H2 density rho2. Then this is the equation. This you should remember for these type of problems. H1 rho1 is equals to H2 rho2. Or we can write in the other way as well. H1 over H2 equals to rho2 over rho1. But I normally remember from this because when we write this, we may confuse us. Right? Like over here comes 1 or 2. So rather H1 rho1 is equals to H2 rho2. To remember this, it will be achieved. Okay. Okay. Now let's come to this problem. We have to highlight this. Okay, so I'll give you as a question here. Find the height of the oil column. Write down. Find the height of the oil column if the height of the water column is the height of the water column is no, manometer is different. You take this and connect to that you use to measure the this one. Yeah, pressure. YouTube is only you take this YouTube. Sorry, those are two different things. Okay, so today we studied barometer and manometer, and this one YouTube. Okay, so in a YouTube, if two liquids are in equilibrium, where their common surface is here. There are other cases also we will discuss, but when the common surface at the middle, so you can write H1 rho 1 is equals to H2 rho 2. By the way, the question is find the height of the oil column if the height of the water column is, let me say, 20 centimeter or 10 centimeter. Height of the water column is 10 centimeter. Okay, find the height of the oil column. If you got the answer, you can share it in the chat box to their knowledge institute. Anyone got the answer? Okay. So we can write H1 rho 1, H0 rho 1 is equals HW rho W. So I want to find H0. So H0 is equals to rho W over rho naught. H0 is equals to rho W over rho naught times HW. Okay, so therefore, rho W is 1000 over 700 into 10 centimeter. So here you can write in centimeter units, totally fine, because here you can see the units cancel of this, then you will get the height in centimeters, right? So not necessary to convert to meters, but again if you take, so it's nothing wrong. So we get 100 divided by 7 centimeters. So 100 divided by 7, how much? 14.285, so 14.3 centimeters. Okay, so the height of this will be 14.3 centimeter. So in meters, if you write this in meters, so centimeter to meter divided by 100, 0.14, 3 round up, so 0.14 meters. Okay, now I'll give you another question. So now this time, say the question, where we have the liquid, okay, so this liquid is filled up here. And this liquid is, okay. So I'll give you the other data. Density, let's say this is rho 1 and so rho 2 actually, and this is rho 1. Okay, and rho 2 is equals to this 2000 kilogram per meter cube. I'll give you this. I'll give you rho 1 as water. For example, this water 1000 kilogram per meter cube. So rho 1 is actually water. Okay, so this is water. And I'll give you the heights. Let's say this height is from here to here. This height, you here like this. 8 centimeter per centimeter. Okay. So all the information is there. Question: find flow 2. Okay. So you have to find the density of this liquid. Whatever the liquid is there, you have to find its density. Here, this is 8 centimeter. 8 centimeter, and this is 12 centimeter on this level. Okay. Okay, I got an answer. Let's check. You guys do the question. I'll be back in a minute. I'll have some water. Okay. Okay. So let us do this question. Now here, what we can do is I consider 2 points. So one is this point, this particular point. I mark that point A, and here this point B. So you can see this is at the surface of point A, and this is, of the liquid water. So this is the same water. So here and here, at the same level, so pressures are same. So I can write PA is equals to PB. So the pressure is at A. I can write it's equals to here the pressure is H1, H2, I say H2, this height H2, rho 2 G, phi equals to pressure here, this height H1, rho 1 G plus phi. So here anyway phi and phi can cancel. I think in the last one, in the first question, I didn't write this add these 5 terms, but then again, you had to add them anyway. It will cancels each other. Okay. So then we have H2 times H2 is so I write H2 rho 2 equals H1 rho 1. So here the H2 is 8 unit of centimeter and rho 2 equals H1 is 12 into 1000. So therefore, rho 2 equals 12 over 8 into 1000. So rho 2 equals 12 divided by 8 is, we can 4 into 3, 4 into 2. So 3 over 2 into 1000. So 1000 divided by 2 is 500, 500 into 3500 kilogram per meter cube. So the answer is 1500 kilogram per meter cube. Okay. Right. Any questions? Okay, so let's move on to the next topic. Density. Actually, density you already know. Mass per unit volume. So density equals, you can write mass divided by volume. So D equals M over V. Okay, so that is density. So the unit we know kg meter cube, and the other units we have SI unit. Other units we have what? Grams per cubic centimeters, and the relation between these two is 1 gram per cubic centimeter is equals to 1000 kilogram per cubic meter. So you can remember this because this is the density of water in this unit. This is density of water in this unit. Okay. So density of water is actually okay. Alright, this equals to density of water. Density of water. Alright. By the way, I'll give you a break at 12 and then we'll continue from 12:30. Okay. Are you all okay with it? Okay. So write the topic after this. Relative density. Relative density. सापेक्ष घनत्व relative density we denote by letter S. Here's the formula for the relative density. Relative density is equals to density of the liquid divided by density of water. So relative density means we express the density of liquid compared to the density of water. So relative to water. Right? Now, for example, let's say a liquid have density same as water. So the relative density is 1. Because 1000 divided by 1000 will be 1. Let's say mercury 13,600 divided by 1000. So the relative density is 13.6. Okay. So over here we write S equals rho divided by rho W. Okay. What is the unit of relative density? Yes, no units because we can see the units cancel. Kilogram per meter cube, kilogram per meter cube cancels. So no units. Okay. No units. Now what about dimension? What about dimension? Yeah, no dimension as well. So it is no dimension also. Okay. So that is relative density. Let's try to do some questions related to relative density. Okay. So S equals rho over. Okay. So here's the question. So I don't prefer giving the question word by word because it will take time. So I will just give you with illustrations. Mm, Question is find the relative density of the liquid. Find the relative density of the liquid. So here the water is the liquid, 5 centimeter, 12 centimeter. The definition for relative density. So it is defined as the ratio, relative density of a liquid is defined as taken the ratio to the density of water. Okay. Or simply you can say density of the liquid divided by density of the water is defined by the relative density of the liquid. Density of the liquid divided by density of water is defined to be the relative density of the liquid. Okay. All right, so let's try to do this. So we can equate the pressure at these 2 points. So we have H1, so H1 rho 1 G plus phi equals to H1 H rho G, H1 rho 1 G plus phi equals to H2 rho 2 G plus phi. So phi and phi cancel, and then G and G cancel. H1 rho 1 and H2 is actually HW. Right? HW into no, so H. I have taken this is H1 rho W is equal to H2 into rho. Okay. So here I want to find relative density. So I take this to the other side. So H1 is equals to rho over rho W into H2. So now what is this? This is the relative density. So H1 height is 12 equals S into H2. S into H2 is 5. So therefore S equals 12 divided by 5, 2.4. So by the way, from this you can write S equals to H1 over H2. Okay. So this height of the water divided by height of the liquid. Okay. So right, W over HL. For these cases, you can write like that: height of water divided by height of liquid. Okay, then so we will have the break now, and again we will join at 12:30. Can you? Yeah. I will do that part after the break. So if you consider the same volume, because the relative density is rho over rho W, density is mass over volume, and then density of water, mass of water, volumes are same. Consider the same volume. Then relative density we can write as mass of the liquid divided by mass of water. In order to write that, the volume has to be same. I will give you that note after the break. So half an hour is okay for you? I mean for everyone? Shall we start at 12:30 or 12:40? All right then, so we will meet again at 12:30. Okay, see you.